Oh.
You can get her 50 cents.
There we go. So, our first term. Two geometric figures are congruent, or the same, figures, if and only if. So, that phrasing, if and only if, they use that a lot in chapter 2, which has to do with like proofs and stuff. So I know it sounds kind of weird in our definitions, but if we would have done chapter 2, you'd be super familiar with if and only if. Which, as a side note, looking at our schedule for the rest of the trimester, we might get to circle back and do some of chapter 2, so that's exciting. Anyway, two geometric figures are congruent figures if and only if there is a rigid motion or a composition of rigid motions that maps one figure onto the other. So, who can remind me what a rigid motion is? I think we've talked about it every single day since we first introduced it. Rigid motion.
It's a transformation that preserves length and angle measure. It maps lines to rate.
Yes, so it preserves length and angle measure. So when we do a rigid motion, then the length of our sides don't change and the angle measures do not change. So congruent figures only happen if there's a rigid motion. We've talked about 3 different rigid motions over the last week, and we quizzed on them yesterday. Reflections, rotations, and translations, thank you, are 3 rigid motions, or a composition of rigid motions. That would be like a reflection, then a translation, or a combination of any of those 3. So that's the only way we can say that we have congruent figures. If we can use one of our rigid motions, one of those 3, or a combination of those 3, to get our new figure. Exactly like we just talked about in warm-up. So a question that you might see is to identify any congruent figures in the coordinate plane. Explain why or why not they're congruent. So if we identify congruent figures, just looking at this, what things are congruent? Do we see right away?
All of them?
All of them. Name them. Which things are congruent?
The squares.
The squares.
The triangles.
So, whoa, slow down. C, B,
Oh.
B, A is congruent to.
Q, P, R, N.
Oh, I totally should have done that in alphabetical order. That's really
Oh my god.
A, B, C, D is congruent to.
Q, P, R, N.
No.
R.
A, B, C, D, E, F, G, H, I, J, K, L, M, N. A, B, C, D, E, F, G, H, I, J, K, L, M, N.
You just started singing the alphabet.
Q, R.
Oh my goodness.
Those are congruent. Now. I don't know.
There's no O.
Doesn't really make sense. Now, this is. Should we go R, Q? A, B, C, D.
Q or S.
L, M,
Got
N,
it.
O, Z, Q, R. Okay, we're good. It says explain. Now, when we explain, we just want to say what happened from here to here. Okay? What happened? What do we see? Did it reflect? Did they rotate? What happened? It translated. So translation. Of what? What happened to the x's?
It went up.
Well, if we start with
X
A,
plus
B, C.
4.
Well, let's start with A, B, C, D.
Minus 4.
So we're trying to get A. Has to get lined up here. So I think it would just be minus 2. You see that?
Oh.
And Y would be what? 1, 3, 4, 5, 6. Y minus 6. So, identifying congruent figures, boom, we just identified one and explain why it's congruent or why not. Is the word congruent funny? What's going on there? Oh, no.
Just move on.
Okay, we'll move on. Let's look at, there's more than 2 congruent things here, but let's look at one more. What else is congruent?
don't know the order of the alphabet.
Okay.
The small triangles, one's in the
The ones in the corners.
one's in the corner, one's in the other
So triangle
corner.
H-I-J is congruent to, oh man, S-T-U? Yeah?
Figure it out.
They can't breathe.
What's not the same size?
The smaller one.
The smaller ones,
They are the same size.
No, they're not.
Yes, they are.
this one
That's smaller than the other one.
and this one.
No. Oh.
What are you
Oh,
talking about?
you're talking about the other ones? You're correct. Yep, you're correct. But we're looking at the other ones. I think it would be
It's corner
UST.
and corner.
What happened? If we're explaining, what happened? A rotation? Yep. How many degrees? 180. Did you say 180?
Yes,
Nice job. Way to go.
I've seen those.
180 degrees. So we identified congruent figures, boom, we did it, and we were explaining what happened. We could talk about what's going on with these two shapes right here. We have a reflection, right?
Yep.
We're reflecting, so we could talk about that as well. If you're doing this problem on your own, which you'll have to do it on practice, but you would want to make sure you include all of those. Another name for a rigid motion, so here's another term. Another name for a rigid motion. Remember, sides stay the same, angles stay the same. Or combination of rigid motions is congruence transformation. Didn't we just talk about that?
Yeah.
So we have congruent figures, are the actual shapes, and the movement of those shapes would be the congruence transformation. All right, so a little bit of a difference there. We just submitted a quiz. Oh, you can see that. Somebody just submitted a quiz. Congruence transformation would be the movement from the pre-image to the image. Like it says, the term rigid motion and congruence transformation are interchangeable, or they are the same thing.
Are your slides posted?
Yes, they are. Questions on that term? Hopefully that's just one to add to the notes where we say rigid motion, aka congruence transformation. Same idea. I'm not sure why I put pictures. So a question you might see, describe a congruence transformation that maps the parallelogram ABC, so the blue, to the parallelogram EFGH, to the green. So this one's going to be a combination. It's going to be two things together. What do we think? What congruence transformation would we need to make the blue map onto the green?
Reflection and translation.
A what?
Is it like?
Yep. So we use, it has to be some combination of
Okay.
translation,
Reflection and translation.
So first, I'm with you.
ABC.
We could reflect across the y-axis. We have A prime, B prime.
There you go.
We would be here, and then reflect, and then arrow, obviously, and we can translate. So move it down. Reflect, or first translate, then reflect.
No, reflect and then translate.
Reflect it down and then translate it over.
Reflect it down. You can't reflect it down.
Yeah, you could reflect across the X.
It goes this way.
Now, one
you can
thing,
reflect it and then reflect it again.
one thing
That's
to
the
note. One thing to note: if we are going to make these congruent, we would need this first point to match up with E. So they would need to match up point for point. We see that? So A prime, oh whoops, not be there. A prime would be here. So if we move it, map it down, translate it down, it would match up with E. So
Yeah.
we know that we are on the right track. Does that make sense? Use the first point of our pre-image to match up with the first point of our image. Questions on that? So if we were describing the congruence transformation, we would say we are reflecting across the y-axis, and then we are translating. We would be translating 1, 2, 3, 4 units down on the y. So y minus 4. All right, here's our two theorems. First one is theorem 4.2. Reflection. Oh, where are the?
Do you
What?
want edited out?
No. Nope.
He's gonna be like, nope, lecture it is.
Now we're good. Do we have those pictures down?
No, I didn't.
What? After all of that, we don't have the pictures down yet? People.
It's so complicated.
Pictures? Yeah, there was a lot going on.
I just took pictures.
Take pictures. These slides are on Canvas
All the
already.
pictures.
Yeah.
The pictures are a lot going on. But the main thing that you need is the parallel lines. Like in the first one, parallel lines, and then those colored lines. And then the second one, yeah, the second one, they're not really the way around that. Unfortunately for you guys, since we are you texting during class?
Just my mom. It really is.
Is it about something that's important? When? 2 weeks. They said tomorrow.
No,
In 2
I
weeks?
turned 18.
What?
Birthday.
Just kidding.
Oh, wait a minute.
All right, we have these down yet.
No, it's slow.
Perfect.
Did you add the images onto the slides on Canvas?
No, I didn't do that. I'll do that during lunch.
Well, what about the online students that don't try to do
They'll be
math?
fine. They'll be fine. If they're, I'll
Send an
know if they're paying
announcement, send an
attention if they notice that that's talking about space. So it's a good test.
Send an announcement
Wait, how
like,
did you
sorry,
notice
I
it
messed
first
up the slides.
Oh, what?
Why did you not notice it first?
First hour eligible.
Oh.
I'm not gonna make that whole thing.
That is smart.
It's the freshmen that aren't on the advanced
Yeah.
track. Yep. So there are. I know you're getting it. I know what you mean. There are some really smart kids in there, but they just
It's just the normal freshmen.
right. They just weren't in advanced math.
We're not the
Right. Okay, I'm going to talk about these because literally I need to talk about these and then we can get you the worksheet. And we'll skip. Unfortunately, we're going to skip the practice problems because I had all the mess ups on the slide, so I'm not going to get to use both my screens for the practice problem. But I will for third hour, so it's all good. Two theorems. First one, 4.2 reflection. It's called reflections in parallel lines theorem. Right on time. I just started talking about the theorems. Good job. You already got them?
What?
You're on it. I like it.
Did you write down
If
the
lines
slides?
K and M, so our lines are here, K and M, if they are parallel, then a reflection in line K followed by a reflection in line M is the same as a translation. So all that to say, we have line AB over here. And if we reflect it 2 times, both times across parallel lines, then it is the exact same as line B double prime, A double prime, or A double prime, B double prime. So these two are the same. They are congruent. It is the same, well, I shouldn't say that they're just the same. It would be the same as just translating B to here and A to here. So double reflection across parallel lines, always congruent. That's all we're talking about. Questions on that first theorem? Because the second one, there's a little more to it. The second one, well, 4.3, reflections in intersecting lines theorem. If, looks like there's an extra I. Lines K and M, so we have K over here, and M right here, so just two lines that intersect at point P, then a reflection in line K. So we're starting down here at AB and a reflection in line K, followed by a reflection on line M. So this time we're reflecting across two lines, but they're not parallel, they intersect. So if we reflect across those two lines, it is the same as a rotation around our original point. So if we have intersecting lines and we reflect across both of them, like we go from the blue to the red to the green, then that would be the exact same as just rotating around that point where they intersect, which in this case is point P. Questions on that before I add one more thing to that here? Last new thing for today. If we look at the measure of B, P, B prime, so right here, this angle, then we say that equals 2x. From here to here would be 2x. Right? We would say that the measure of just straight up x, right here, M, P, K. So what they might do in a problem is that they might tell you that this is like 20 degrees in blue, and they might say, what's the measure of angle B, P, or B double prime P, B? This outside, whoa, what's the measure of this outside angle? Well, it would just be 2 times 20, so it would be 40 degrees. Do we see that? Or is that a little bit confusing? Kind of confusing? So it would be like this practice problem. Find the angle of rotation that makes A this point, this triangle, map onto A double prime. Well, like we said, inside this intersection, we would consider that to be x. I get if you have to send one text to your mom or something like that, but we just can't be consistently, especially when we're talking on our phones during class. Otherwise, I told this in the third hour too, we'll just have a phone stack in front of class. That would be cool. But to get A to A double prime, the inside of these angles is 55 degrees. So if we want to find the measure from of the whole thing, the measure that in this case, like they put it, that rotates A all the way over to A prime, it would just be 2 times 55. So we get 110. Do we understand the idea that it's getting at? Yeah, Anastasia?
Where you get to those?
So up here in our theorem, they told us that from here all the way to here, so that whole rotation, that they refer to that as 2x, okay? Or you could say it's 2 times the distance from inside where those lines intersect. I kind of put a lot on there so you can see. But you see where these lines intersect right here? We would consider that to be x on the inside of the intersection, and we would consider what we do to get from B to B prime, that would be 2x. So double the distance. That's all it's trying to say. That's double the distance. And we'll have a little bit of practice with that on the homework. Questions, comments, concerns? It says we're at 28 minutes. This was supposed to be like a 12-minute lesson. So some technical difficulties might have played into that, but that's okay.
A little bit.
I'll try to cut it for the online. For the online students.